So, hi, I'm Kara. I don't know if you heard that, or Karamarie, either one is fine with me. For today, I'll be speaking about RoboCop, which stands for Reasoning Over Biomedical Objects, Linked to Knowledge-Oriented Pathways. RoboCop is funded jointly by NIHS and the NIH Office of Data Science Strategy, and the prototype was funded by NCATS. And I'll be focusing specifically on how RoboCop leverages ontologies for data normalization, integration, and query. So we all know knowledge graphs are everywhere, not only in popular search engines like Google, but in a variety of applications, some of which are listed here. Just as a quick reminder, the basic unit of knowledge in a knowledge graph is the subject, predicate, object triple. And in the example provided here, there's just a simple triple of Da Vinci painted Mona Lisa. But I'll be focusing on RoboCop, which is a biomedical knowledge graph system. And it's modular, it's publicly accessible, and it's comprised of several different core components, the key ones listed here. So there's a front-end user interface, there's the RoboCop knowledge graph itself, there's a variety of API endpoints to query the knowledge graph. There's also a collection of standardized and interoperable knowledge graphs, including those that are ingested and harmonized into the RoboCop knowledge graph. And then there's a bunch of supporting tools and functionalities, such as an enrichment function. The RoboCop knowledge graph, a high-level schema shown on the right, currently contains about 10 million nodes and 130 million edges drawn from more than 40 biomedical data sources and biontologies, including some of the examples shown here. So comparative toxicogenomics database, or CTD, drug bank, binding database, monarch disease ontology, gene ontology, human phenotype ontology, and many others. So the RoboCop knowledge graph can be queried via the user interface. So shown here on the bottom left is a Welcome to RoboCop landing page, which is linked out from the main landing page of the UI and allows users to view example queries, to explore templated queries, or to create their own query. And if you click on that, create your query, it takes you to the RoboCop question builder. In here, users can create their own query graph using either the fields on the left or the bubble graph on the right. Users can also upload their own query in JSON format. After submitting the query, the user will be taken to the RoboCop Answer Explorer tool, which I'll show you when I review a use case example application. But regardless of how users query RoboCop, the key point here for this presentation is that RoboCop supports ontology-driven query and answer exploration. And how RoboCop achieves that is through a very robust socio-technical foundation to overcome the many challenges involved in creating biomedical knowledge graphs. So, for instance, there's a lack of standards and schemas and data models. There's multiple ontologies and identifier systems for the same or similar biomedical concepts. There's a bunch of different disparate and overlapping terminologies and vocabularies, and there's different ways to model basic biomedical concepts, such as chemical versus chemical exposure or drug formulation. BioLink model, name resolver, and node normalizer, Orion, and DMOG provide the foundation that allows RoboCop to support ontology-driven, to overcome these challenges and support ontology-driven query and answer exploration. And I'll walk through each of these briefly here. So BioLink model, we've adopted as a community-driven standard that essentially leverages both control vocabularies and ontologies as an upper-level ontology. So we heard about Solu earlier today. BioLink model is very complementary, and I think, in fact, some of the same people are developing the two ontologies, whereas Solu is more foundational and high-level. BioLink model is more of a graph data model and schema very specific to the biomedical domain. And it supports semantic harmonization across disparate biomedical data sets and ontologies. The model expresses domain knowledge as an hierarchical graph of relationships between biomedical entities. So shown on the right is just a very brief portion of the BioLink model. Category tree, you can see at the root of the tree, there's just this generic name thing, and then the biomedical categories or classes get more specific as you dive deeper down the hierarchy. In addition to adopting BioLink model, our team, in collaboration with a lot of other teams, has invested a lot of resources into two key tools to support and overcome the challenges of entity resolution: name resolver and node normalizer. So both of these tools leverage BioLink model and can be accessed programmatically. Name resolver takes lexical strings and attempts to map them to BioLink preferred identifiers as well as to BioLink model categories. So in the example shown here, the input is clofibrate, and you can see a partial output. Node normalizer takes an identifier and returns the BioLink preferred identifier, all other equivalent identifiers, and the BioLink semantic type for that entity. In the example here, we see KEBI 3750, which is the identifier for clofibrate. Orion, or operational routine for the ingest and output of networks, is a custom software pipeline that leverages BioLink model and tools like Node Normalizer to ingest Robocop's underlying knowledge sources, semantically harmonize them, and output them as a collection of harmonized and interoperable knowledge graphs, including the Robocop knowledge graph. And finally, DMOG, or the Data Management Oversight Group, is a key component to Robocop's socio-technical foundation. So DMOG is comprised of select members of the Robocop team and provides governance and data prioritization. They have a formal process in place for quantitatively evaluating proposed data or knowledge sources using a variety of criteria, including the ones listed here. And based upon that process, they prioritize new knowledge sources for Orion ingest. So I think at this point, I'm going to turn to highlight Robocop's ontology-supported query and answer exploration capabilities in the context of a real-world use case contributed by the Undiagnosed Disease Network. So the UDN is an ongoing prospective study of participants who have some sort of inexplicable illness that has not been diagnosed at the time of study enrollment. After enrollment, participants complete an environmental exposure survey and they undergo very deep clinical diagnostics. In a lot of cases, they do receive a diagnosis and effective clinical management of their condition. But in a significant proportion, despite the deep clinical diagnosis, UDN investigators can't diagnose some of these patients, and they remain undiagnosed. And so Robocop was brought in. The UDN investigators came to Robocop to see if we could use Robocop to sort of look at what other factors, specifically environmental determinants, may be accounting for disease in these undiagnosed participants. In the example I'll show here, I'll focus on one participant, UDN 235962. This is a male pediatric participant. There is a suspected gene that the UDN investigators have identified, EZH2. Again, no diagnosis despite all the extensive clinical phenotyping, but they do have a phenotypic profile comprised of about 30 different phenotypes that UDN investigators map to HPO terms, or human phenotype ontology terms. So we then went to the Robocop question builder, and we just asked a very simple question. What chemical entities are related to this gene of interest, EZH2? Robocop returned over 3,000 chemical entities. The top ranked and scored answers are shown in the screenshot on the right. And importantly to note, we queried for chemical entity, but Robocop returned, in the examples that are highlighted in dotted lines, BioLink drug, in this case, tretinoin, and BioLink small molecule, which in this case is CPI 1205. So we queried for something more high level, and because of the BioLink hierarchy, Robocop was able to return more specific results than what we asked for. So that we were essentially able to ask a query that allows us to explore both small molecules and drugs, not just chemical exposures. Of interest to our use case, one of the top 12 answers was for bisphenol A, which is an environmental hazard produced in large quantities during the production of polycarbonate plastics. And so this was of interest to our team. So we took a deeper look at the Robocop answer subgraph for bisphenol A. And we found that Robocop returned 4 edges supporting the connection between bisphenol A and EZH2. one of those edges was stated effects. And when we clicked on the edges, we could see the full provenance of those results, including the primary source that contributed that assertion, which in this case was CTD. And we also see that effects, which is more specific than again, the predicate we queried on, which was related to, but it was actually additionally qualified to have a qualified triple, which is shown as on the right as bisphenol A increases molecular interaction with EZH2. So RoboCup also returned an edge with the predicate occurs together in literature with. This edge was contributed by a RoboCup service called OmniCore, which exposes as edges with that particular predicate and counts of co-occurrences of entities derived from PubMed abstracts. So RoboCup adds OmniCore edges to 2 entities in results when available. Those edges not only provide users with additional evidence for RoboCup assertions, but they also are used in RoboCup's scoring and ranking algorithm. So given the large number of phenotypes with this particular UDN participant, as again I said, there's like greater than 30, we decided to apply RoboCup's enrichment algorithm to the phenotypes. And so we applied that enrichment algorithm, and then we further narrowed down the results by filtering for the suspected gene of interest, EZH2. The top ranked answer in this case was for Weaver syndrome, also known as Weaver-Smith syndrome, which is a rare genetic disorder characterized by accelerated growth, distinctive facial features, and various intellectual disabilities. When we looked at the predicate, it was biolink causes. And we thought that maybe this is, this syndrome actually is caused, when we look deeper into the provenance, by the mutations in that gene, EZH2. So we thought this may potentially be a disease of interest. As such, we use the RoboCup question answer builder to generate an AOP, or an adverse outcome pathway. And we just asked what might connect biological processes, genes might connect bisphenol A to Weaver syndrome. And so we found one of the top answer subgraphs was shown on the bottom left corner. And then there's a high level natural language interpretation shown on the right. In this case, the AOP asserted that bisphenol A decreases the expression of GABRA1, or GABA receptor subtype A1, which is actively involved in GABA signaling, which is negatively correlated with bilateral clonic-tonic seizure, which is a phenotype of Weaver syndrome. Of relevance to this use case, the participant's phenotypic profile did include seizures. So in addition to supporting ontology-driven query and answer exploration, RoboCup provides actionable insights. So in this example here, RoboCup suggested that perhaps the UDN participant and/or biological mother had a history of exposure to bisphenol A. Perhaps the UDN participant has Weaver syndrome. So maybe RoboCup was able to identify a diagnosis for this patient. But we don't know that for sure at this point in time. So we are now working with UDN investigators to explore whether we can find evidence of bisphenol A exposure in the participants' environmental exposure survey data and/or clinical assessment records. We did put forward the hypothesis that maybe this particular participation has a diagnosis of Weaver syndrome. And while I highlighted bisphenol A here, RoboCup returned a number of additional chemical exposures that may be associated with the participant's phenotypic profile, and we're currently exploring them. And with that, I will acknowledge our team and our funders, and thank you all for your time. Please feel free to reach out to me should you have any questions or want to learn more about RoboCup.